So thank you everybody for joining. This is our last seminar series before we start fieldwork this summer. And Paul is joining us remotely from Denver, and he's going to give us a talk on the geology of the San Juans and gold and base metal deposits that he mapped up there. When was that? During the 80s or 70s? It's a long time ago.
80s.
Yeah. I worked with Paul at Anglo Gold Ashanti, and he's a good friend, and I consider him a mentor. And more recently, Paul was one of the recipients that their coveted Thayer Lindsay Award that PDAC handed out this year. So it's a great honor to receive that award, and it's also a great honor for you to join us today, Paul. So thank you.
Well, thanks for having me. Apologize for the technical difficulties. You guys don't hear an echo, right? Hello?
Yeah, I'm going to mute our end, Paul, so that the other people online don't hear an echo coming from us.
Okay. Are you guys good? Is everything? Can you hear me?
Yes, go ahead.
Okay. Well, again, thanks for putting up with all this technical hoo-ha. We'll get going now. So this is a map by Kelly, 1943, and Kelly was a very detailed worker. And all those red lines are quartz, sphalerite, galena, tetrahedrite veins. And they're not all of them. Okay, this is only San Juan County. The Hinsdale County to the north, Kelly ran out of time and he doesn't map them. So you're looking at more or less, so there's probably another 30% or more veins in Hinsdale. So you're looking at 1,000 some odd veins. And for a first order approximation, and we're going to get into some of the details in this talk, these veins are all the same. They are quartz, sphalerite, galena, tetrahedrite veins. If you use your LS, they're IS type veins. I'm not a great fan of calling intermediate sulfidation veins, but a lot of people use that terminology. They have, not only do they look the same, they have the same alteration, they have the same paragenesis, and we're going to get into this in a little more detail. Fluid inclusions and all isotopes and this sort of stuff all generally come out the same. So when you're thinking about how veins form, where the metal comes from, you have to consider this kind of place, right? So how do you generate a vein field? And you see the scale bar here, right? So this is a 2 county-wide vein field, all pretty much the same. And now we're going to get into some of the details. Okay, so this is, I realize there's a table of numbers and that's not the most thrilling thing you want to look at. But the point is a lot of metal. In 2024 dollars, that's 12.5 billion. Of course, gold, since, as you know, gold's gone up to 5,000 an ounce, silver more than 90 an ounce, so this number is way obsolete. But I think you get the gist. And so of all this tons, the 42 million tons, 8.5 million ounces of gold, and 175 million ounces of silver, there were 4 big mines that generated the vast majority of the revenue. And they are the Camp Bird, Idorado, Shenandoah Dives, and Sunnyside. And what did those mines have that all the other mines, and there's more, as you saw, there's 1,000 some odd veins, and multiple thousands of workings. Why those 4 mines? Because those 4 mines had gold. Okay, I'm going to show you in the next slide or the slide after that the grades of this region. But those 4 mines had gold, and that's what drove their production. Okay, the last one here, Ulay, is probably the best of the rest. Okay, and if you look at Ulay's numbers, I mean, it's respectable with respect to silver. So 5.25 million ounces of silver, trivial amounts of gold, and you can see a little, you know, some lead mostly, some copper, some zinc. We can explain Ulay fairly straightforwardly, because Ulay happens to be a vein. The normal vein thickness in the San Juans is about 3 feet. Ulay was 5 to 10 feet, getting up to 15 feet across. A strike length, a normal San Juan vein is on the order of 800 feet. Ulay was 2,400 feet. So it's pretty easy to understand why Ulay was one of the best of the rest, simply because it was one of the bigger veins. Okay, it wasn't a richer vein, it just was a bigger vein. But the other 4, the big 4, had gold. Okay, and so the question as an explorationist, and that's what I am, is why did those 4 have gold and the other 1,000 quartz veins did not? And once we understand that, then where do we go to look to find some more, right? Okay, so what are we talking about? We're going to talk about 3 districts today. Here's Sunnyside. We're going to talk about the Mineral Point area, which is where I did a lot of the detailed mapping. And we're going to talk about Lake City. And here is Ulay. And in case you're wondering where the other gold-rich veins are, is Camp Bird is here, Idorado is here, and Shenandoah Dives is there. I assume you guys can see the pointer. If not, okay, I'm wasting my time. Okay, let's give you some general geology. Here is where we're talking about. This is the southwest corner of Colorado. I like this particular figure from Stanford because it simplifies a rather complex geologic picture. But what we've got is, starting at about 33 million years ago, we've got 4 major andesitic stratovolcanoes. You know, your standard arc-type andesites. Those were followed by 4 nested calderas. These are granodioritic to rhyolitic in composition, mostly granodioritic. San Juan, Lake City, Uncompahgre, I forgot the other one already. And then there was a whole series of intrusives, which ranged in composition from dacite to alkalic rhyolite. So, and of interest, and I don't think it's a definite coincidence, and there's a reason for that. All the veins generally are in this area where we see all the intrusions. Okay, so now if you're, just to step back for a minute, so if you're thinking on a tectonic point of view, this area is basically quiet, since the Proterozoic, and there were some Paleozoic seds. And then all of a sudden there was a blowtorch underneath the crust, starting at about 33 MA, continuing to about 10. And then it shut itself off. Okay, so the explanation for this is flat slab to subduction, a piece of the slab, which is, and you have to understand why the flat slab, because you've got andesitic volcanism way far from the continental margin. right? So how do you get andesites basically in Colorado? So they invoke a flat slab. The idea is part of this slab detaches, and that's kind of what's turning on the blast or the Bunsen burner beneath the crust. And then until that piece is digested, you have all this activity. Okay. Now we get into the details of the 3 districts. And so let's start with the grades. So if you compare Sunnyside to, this is Mineral Point to Lake City, which is also known as Galena. Sunnyside has an order of magnitude more gold than Mineral Point, and almost 2 orders of magnitude more gold than Lake City. Okay, I should emphasize that these grades represent averages from hundreds of mines, historical records, right? So this is the average of the district. But what's interesting is look at the silver, which is essentially the same, 1.6, 1.9, 1.8. Look at the copper, 0.2, 0.1, 0.1. Look at the lead, 2, 2.3, 3.0. Okay, so you got a little more lead in the Lake City area. Zinc is kind of odd, and the numbers don't work very well for zinc for the simple reason that zinc was not an economic commodity up until about 1900, 1905. So the historical record is skewed with respect to zinc grades. But having pounded the rocks, I can tell you that the zinc grades are comparable. And so then you look at the production, right? So Sunnyside, nearly 7 million tons. Mineral Point, 20,000. Lake City, 18. What's the big difference? Gold, right? That's the huge driver here. Look at the paragenesis, and this is important. And I'll show you document this. So we'll start with Mineral Point. You have an early quartz pyrite stage. You have banded quartz sulfides, which is basically sphalerite galena tetrahedrite. This is where the silver comes in. You've got manganese, either rhodochrosite, manganocalcite, rhodonite. At Lake City, we see the same thing. Early pyrite quartz, the quartz, lead, zinc, silver. Here's the rhodochrosite. Okay, Lake City has a little lake fluorite. Sunnyside, early quartz pyrite, banded sulfide, massive sulfide, basically sphalerite, galena tetrahedrite. Here's the gold. We'll talk about that in a minute. Here's manganese. And then again, lake fluorite, calcite fluorite. So you've got 3 districts, spatially quite removed, with basically the same paragenesis. So if you're going to think about this field, you got to kind of think about, okay, how is this working, right? How is this working that you're having exactly the same kind of paragenesis? Here's the same sort of textures. Here's the same sort of alteration. We can look at the fluid occlusions. Sunnyside's a little bit hotter, but you can compare Mineral Point to Lake City, and it's 244 to 233, right? If you look at the iron composition in sphalerite, it's basically the same. And then we'll talk about boiling. So this gets back to the point that the real difference between these 3 things is, for whatever reason, Sunnyside has an order of magnitude to almost 2 order of magnitude more gold. And the question is why? So let's just go to Mineral Point. So this is the commute. Nice commute. Rugged area. I should mention that when we're talking grades, because it's severely mountainous and glaciated, we don't have to worry too much about supergene effects because the glaciers have stripped off any kind of supergene oxidation and, you know, excluding a very thin skin. So we're talking hypogene grades. And I will say these slides are old. Now this place is overrun with razors and tourists, and it's not quite as wide open and no one there as it once was. Here's the mineral point area. Pretty easy to map the veins. You can see the long linears. Okay, some color scars here, some color scars there. Pretty easy place to map, frankly. So this is the map that I generated. And I think you could get an idea why I was there. This area, Mineral Point, was well known in the literature, Ransom 1909, for having the highest vein density in the entire San Juans, Western San Juans. And so our idea was basically very straightforward. If all these veins, all these black lines are veins, right? If all those lines carry some values, don't have to be ore grade values, you know, back in 1909, but carry value, then you have a block tonnage opportunity, right? Because you could just jump on this area of high vein density and potentially turn it into a block tonnage operation. Well, it's a fine idea. It didn't work out for the simple reason that most of the veins are dead. Okay, so so the way it works is, remember you had your 3 paragenetic stages. So in this diagram here, I'm documenting the different paragenetic stages. So where you see black, it's just quartz with some pyrite and basically no gold, no silver. No lead or zinc either, for that matter. The blue shows ore shoots of sphalerite galena tetrahedrite. So that's where your silver is going to reside. The red is showing manganese. And the important point of this, there's a little note down there. So where you have red, you also have blue. So the interpretation is that this fracture system was open and progressively filled in with the different paragenetic stages. So you had early quartz, pyrite, and that sealed off a lot of these structures. Some of it stayed open, and we got ore shoots in sphalerite galena tetrahedrite. And then some of them remained open and got the late stage manganese minerals. Okay. So let's well, this is just what I said, that this is the general paragenesis, early quartz pyrite. Here's where the goodies are as far as lead, zinc, silver, and then the manganese at the end. Very simplistic kind of paragenesis. This is what the stuff looks like. This is early quartz pyrite, not much pyrite in this rock, but there is some. Here's a classic paragenesis. The gray is the andesite wall rock that has been pervasively cerussitized to quartz sericite pyrite. And you can see here's the sphalerite galena, early quartz, and then we're picking up later in time the massive sphalerite galena. Okay. Here's that massive sphalerite galena cut by pink rhodochrosite. And you could pretty clearly see that paragenetic relationship. The gray here is mostly galena, some sphalerite. And I think, unless you're colorblind, it's a fairly easy paragenetic sequence to unravel. Okay. This is Houghton Mountain. It's the highest point in the Mineral Point area. It comes up at, I think it was 13.5. Yeah. And what's important about this is you can see the veins cutting all the way up to the top of the mountain. So what this does is, and I've walked this, and back in my younger days, I think now I'd be a little more leery, but back then I was a billy goat. You could see what the veins look like as they approach the paleo surface, right? So here you have a well-defined quartz vein showing shoots, dominantly sphalerite galena tetrahedrite. It gets gold rich toward the top, or silver rich, pardon me. But what we see is a fairly tight sericitic halo. That's this green with the sericite pyrite quartz. And then as we approach the surface or approach the top of Houghton Mountain, the veins horsetail. You don't see the tight sericite. Instead, you get a broader, weak sericitic alteration in that you can still see relic texture, which you couldn't see at depth. You still have some chlorite in the mafic sites, which you also didn't see at depth. The important thing about this is, okay, so you see these things fingering out, but never do you see an illite cap. Okay, such as occurs at Creed or at Guanajuato or at Oatman or any of the classic low sulfidation quartz adularia systems. There is no evidence of an illite cap. There is no evidence of adularia. Okay, two more things commonly used to invoke boiling. Okay, and that is supported by the fluid inclusion and isotope data, which was gathered by Jack Bloom in the 90s. Okay, so here's his fluid inclusion numbers, about 244 average. You could actually work out a vertical zonation, so it's getting cooler as it goes up higher, which makes sense. No boiling, no evidence of boiling in the fluid inclusions. You kind of got a scatter of salinity. Oxygen isotopes suggest meteoric water, no magmatic inputs. Okay, lead isotopes suggest lead from the basement. And now I could produce a slide from Lake City, and I'm just sparing you the slide, and it would read exactly the same. The fluid inclusions are basically the same number, no boiling, same salinities, no evidence of magmatic input, lead isotopes, lead from the basement. Okay, so you can take all this data, and what does it suggest? It suggests heated meteoric water, metals coming from the basement, deposition probably by simple cooling, probably mixing with groundwater as you get higher up. Okay, there's a new theory about mineral deposition by Mario Guzman and some of Thomas Monique's students, and Mario was a Monique student, about fluid flashing, which is the idea that under pressure in a standard geothermal system, if you suddenly release the pressure, say through a fault, that fluid would flash boil, not simple boiling, but flash boil, and that would cause deposition. It's possible, but I see no evidence for flashing at Mineral Point. Okay, let's turn now to Sunnyside. So we were at here's Mineral Point. Here's Sunnyside down there. So a few miles away, that scale bar is miles. And just to reiterate, here's the production, nearly 400,000 ounces gold, 11 million ounces silver. Here's its grade. Here are some of the details. I think we'll skip through some of this. This is the mine plan of the Sunnyside mine. Okay, this is what the veins look like. And okay, so this is in I forgot the name of the basin already. Anyhow, you can see the vein. This is the no-name vein zinging off through the countryside. The iron stained bit is quartz with some sulfides. The black is pyroxmangite, a manganese mineral. And this is kind of a close-up. So it oxidizes to the sooty black, but if you whack on it, inside it's actually a nice bubblegum pink. And it makes beautiful cabochons and this sort of things. So this vein here is 10 feet, 12 feet across. And it looks pretty similar to what we saw at Mineral Point. And now we'll look at some paragenesis. Massive sulfide, this is galena. You can see the chalcopyrite cut by late rhodonite. Well, technically it's pyroxmangite, but rhodonite is what's in the literature. There's a small crystallographic difference, but informal usage in this district is rhodonite, but if you want, technically it's pyroxmangite. Okay, how does the gold fit in? Here's slabs from Sunnyside. Here's massive sulfide, right? You can see the galena, you can see the pyrite. Gold is clearly after the sulfide stage. Nice shiny gold with quartz. And here, I don't know if you could see the specks of gold. Here you have late manganese, the pink, cross-cutting the quartz gold. So we got the gold pretty well constrained. It comes after the lead, zinc, silver. That's sphalerite, galena, tetrahedrite, but before the manganese. Okay, again, so how does this work? Okay, so there was a famous paper by Casaval and Omoto, and I can't emphasize how much traction this paper got. Casaval was at that time he was a young PhD student. Hiroshi Emoto was a physical chemist, and what they did was basically do a whole series of very elegant experiments showing how boiling, simple boiling. This is the idea, just to make clear what simple boiling is. This is like you're cooking up some spaghetti. You got a pot of water. You turn on the burner. Eventually the water boils. Okay, so just with that kind of model, of course, at 250 degrees C acidic fluids, they showed through a series of very elegant experiments that if you boiled an ore fluid at 250 Cs, you could deposit gold. Okay. This was very well received by the industry because for a long time people had speculated that boiling was an important depositional mechanism, particularly in quartz adularia vein systems, say your Tonopah, your Comstock, but no one really knew how it worked. Everybody said, yeah, we think this is what's going on, but no one knew how it worked. Well, Casaval and Omoto showed how it worked. But there was just one small problem. They actually didn't demonstrate that Sunnyside boiled. They said it did. If you actually go read their paper, the fluid inclusion evidence demonstrating boiling at Sunnyside is extremely weak. There was one sample that boiled, and that was from the late fluorite stuff and not the gold stage. Okay, but that was sort of overlooked. Okay, and so when Casaval and Emoto's paper came out, everybody said, this is great. Okay, so now with respect to the San Juans, you got 1,000 veins, right? All we have to do is find those veins that boiled, and shazam, we'd have a gold mine, literally. Okay, if on the other hand, boiling wasn't the depositional mechanism, then you're wasting a lot of time and money chasing the wrong thing. So now the other interesting bit between the three districts is that Sunnyside has a distinctly younger age than Mineral Point and Lake City. And there's the numbers there. So Mineral Point and Lake City, despite being 10, 15 miles apart, basically formed at the same time. Sunnyside formed, as you can see here, almost 10 million years younger, 10 to 8. And yet, that's the key, right? And yet the mineralogy, the paragenesis is essentially the same. So when you're thinking about how do veins form, how do you manage to do that, right? You got one system forming 8 million years younger than other two, and yet on visually and most other of your criteria, it's essentially the same kind of system. Okay, the other thing that's happening at Sunnyside time, it turns out the other three of the big four, Idorado, Camp-Bird, Shenandoah-Dives, also formed. So the gold-rich guys, the big four, are forming distinctly younger than the likely rest of the San Juan vein systems, right? Because remember, we got 1,000 veins. Now, not all of them have been age dated, obviously. And I suspect if you went out there and grabbed samples, maybe we get a bigger spread. But what it looks like is that the four gold guys are younger than the standard quartz, sphalerite, galena, tetrahedrite vein. So what else is happening at that time? Rhyolites, particularly alkalic rhyolites. So then that, drives the obvious, well, here's the summary, right? So Sunnyside has an order of magnitude more gold than the other two districts, but the same amount of base metals and the same amount of silver. Sunnyside is distinctly younger. Sunnyside is 50 degrees hotter. Okay, does that make a difference? According to thermodynamically, it shouldn't, but maybe it does. Okay, no evidence of boiling whatsoever in Mineral Point or Lake City. Sunnyside, we got a question mark, right? Everything else is the same. Salinities, alteration, paragenesis, lead isotopes. So this leads to a model, right? And so my interpretation of this is that the gold at Sunnyside is directly related to alkalic rhyolites. Okay, the rest of the metals, with the exception of tellurium, the rest of the metals are coming from the crust in a system similar, if not identical, to Lake City or Mineral Point. But Sunnyside has a little more juice coming from that alkalic rhyolite, and that alkalic rhyolite is contributing gold, tellurium, and a little moly. So do we have any evidence for this? Well, we come close. Okay, the age is the same. There's a nitrogen-argon ratio study, a preliminary study, suggesting magmatic volatiles at Sunnyside. Remember, we have no evidence for magmatic contribution at Lake City or Mineral Point. Mario Guzman has now found B veins at deep beneath Sunnyside. For those who aren't familiar with B veins, this is a porphyry copper interpretation and basically indicates proximity to a mineralizing intrusive. Okay, he doesn't have the intrusive. And Mario's interpretation is they just missed, the proverbial missed it by that much in the drill core. But he's claiming these B veins with saline inclusions, etc., high temperature, is reflecting a porphyry style kind of event, which is driving the Sunnyside system. There's also magnetotellurics suggesting an intrusive below Sunnyside. So we don't have the smoking gun, we don't have the intrusive, but boy, it sure looks like there's something down there that's driving it, specific it. And I will argue it's probably an alkalic rhyolite. So now, you guys are now experts on Western San Juans, courtesy of listening to me babble for half an hour. So we'll do a little, where would you, here you have this map. And I'm going to ask you to put on your exploration hat. Where would you drill, or would you drill, and why? Okay, and we'll make the assumption that land acquisition is no problem, etc. So I'm going to throw this up here for a couple of seconds and let you guys stew on it, because this is the kind of thing that I do. And I think it's fun. So I'll give you a few seconds. And so if you look at this map, and it's pretty obvious, I think the direction of maximum fluid flow is probably northeast, right? Because you look at where all the chutes are. They're mostly oriented at either north-northeast or northeast. But the question for you guys is, would you drill this thing for a Sunnyside type occurrence? Okay, remembering what we know about the paragenesis. And I will tell you one other thing, which isn't obvious on this map. The gold-rich chutes at Sunnyside tend to occur at the top of the Burns Formation near the contact with the Henson. And this is exactly where we are. So we're in the right rocks. We're at the top of the Burns Formation in the Henson at the right elevation. So again, I'll toss it back, and I'm not going to ask for a show of hands or any of that, because that's impossible on Zoom, but just you can think about it. And I'll tell you what we concluded. And my conclusion was very simple, was where everything was right, there's no gold. Particularly if we think about the paragenesis, we know that the manganese at Sunnyside comes after the gold stage. And so the question is, if we've got manganese here, where's the gold? Well, I would argue it's not there. Okay, and Noranda subsequently popped a half a dozen holes at the southern end. I hope you can see the cursor. Down in this zone, what did they hit? They hit veins that had the same grades as exposed on the surface. They didn't find any gold either. Okay, so that's sort of the summary of the model and the veins. And so to conclude, we'll talk a little more about Sunnyside, and Sunnyside's kind of fun. Here's this nice name, Sunnyside, walk on the sunny side of the street. And yet, really, what Sunnyside is best known for are two major catastrophes. And they are true catastrophes. And catastrophes are fun to talk about as long as they don't happen to you. So we'll dive into the catastrophes. This is a historic shot of the Sunnyside mine. And it's sitting on the shores of Lake Emma, which is this nice lake at, I forgot what elevation it is, 13,000 feet, something like that. Okay, well, one fine day, to be precise, June 4th, 1978, they punctured Lake Emma, and it drained through the workings. And it's literally like pulling the plug in a bathtub. So literally 500 million gallons of lake water entered those workings in the course of about 5 to 10 minutes. A giant draining of a bathtub. Amazingly enough, no one was killed. Now, at the time, they had about 150 people working underground. They worked 6 days a week, and the lake punctured through on the one day that they weren't working, on Sunday. So what are the odds? Well, 1 in 7, right? Because 6 days a week. And had it punctured when those guys were working, with the exception of maybe 1 or 2 who could have found an air pocket or something, all of them would have died. Okay, as it is, they dodged a huge, huge bullet. It drove the company into bankruptcy. It was a disaster. But you didn't have 150 people dead. So this is, I was just back up there last fall, actually in August. This is the site of Lake Emma, and if you can kind of look at the topography, you can kind of see the lake would have been about here. And you can see some of the color scars from some of the veins. But you'll notice there's something missing. There's no water. Okay? It's had, whatever it is, 25, it's had 50 years to fill back up. There's no water. Why? Okay, well, we'll talk about that. But let's talk about how they screwed up. Okay, so first you're thinking, geez, did they not know they were under the lake? Well, yeah, they knew. Okay, here's the vein. It was on the spur drift. I hope you could see the outline of the lake. So they knew exactly where it was. And in fact, they were worried about the lake. Because just prior to when the lake punching through, they sent the mining engineer out into the lake in a little inflatable boat with a plumb bob to measure the depth of the lake. Now, why were they doing that? Because they wanted to make sure they had enough back so that they could mine under the lake without it popping through. Okay, well, fine. If all that is fine, there are calculations, by the way, for those who aren't mining engineers. There are calculations based on mines such as the tin mines in Cornwall, where they actually mine under the ocean, how much back you need to keep the ocean from punching through your workings. And they would have had enough back if, and that's a big if, there was solid rock all the way under the lake. Unfortunately, there wasn't. And you can see that here. Here's Lake Emma, and most of it was not solid rock. In fact, they had very little solid rock. Okay, so could they have known this? Well, yes. A, they didn't map the bloody lake. You know, they sent the mining engineer out with his plumb bob. If they'd asked him to mine the lake, he would have seen that one shore was solid rock that had the gold vein in it. The other shore was glacial debris. And then if you would have asked the question, how did the lake get there in the first place? Okay, Lake Emma is a paternoster lake. This is a glacial geologist term. And basically, think of the glacier as a bulldozer blade. So it scrapes a hole and then stacks a whole bunch of boulders and stuff on the side, right? And so the bottom of the lake, which is what you want to know, is the bottom of the lake hard rock, or is it a bunch of glacial debris? Okay, and if it's a bunch of glacial debris, why is the water still there? Okay, well, the reason the water's still there is this: mud. Okay, so when that thing burst through, all the mud at the bottom of Lake Emma that has been accumulating since the glacier left 12,000 years ago, maybe 11,000, all under the mine. And this poor guy, they literally spent 2 years getting all the mud out of the mine. Okay, and I think it's this mud that acted as the seal and kept that water there. So if you can imagine Lake Emma, it's like it's sitting in a bowl of Jello, and the only thing that stopped it leaking was all this goopy mud. And once it broke through, whoosh, all the water flowed through, all the mud entered the mine. Okay. The company that was operating at the time was called Standard Metals. As I mentioned, puncturing Lake Emma drove them into bankruptcy. The mine was then bought by a bunch called Echo Bay. Incidentally, I actually looked at the Sunnyside mine as a potential acquisition. I was working for Asarco at the time. I didn't think there was much reserves left, so we passed on Sunnyside, but Echo Bay didn't. Okay, and then eventually Echo Bay was bought out by a firm called Kinross. Okay, and Sunnyside was basically a throw-in. Kinross really wanted another mine called Lubin and McCoy Cove, and in order to do the deal, Echo Bay said, "Well, take Sunnyside too." Okay, so they did. And one of the interesting things between then and now is, I will say, and I can say to this because when we did the evaluation, you weren't so much worried about the environmental liability, which is not the case now. Okay, very different set of circumstances not that long ago. So let's talk about, so in 1995, well, in 1990, the mine closed. They ran out of ore. And Kinross wanted to put the mine to bed. Okay, and so basically, let me back up. In 1960, this tunnel was put in to access the deeper parts of the Sunnyside mine. Okay, why did they put in this tunnel? They wanted to do two things. The mill was located on the side of a mountain, severe switchback roads, in an area with heavy winter snows and just really nasty weather. It's a terrible place. By putting in this tunnel and allowing all the ore to come out here, you're now on the valley floor, which, even though it's at 10,500 feet, is a heck of a lot better than up at 12,000 feet, and much safer. Nice valley, no problems. So logistically, it made a lot of sense. It also dewatered the mine because Sunnyside was a wet mine. Okay, in so doing, they created a point source discharge, because now all the water, the groundwater, rainwater is going to work its way through the mine, interact with all that sericitic alteration, pyrite and sericitic alteration. It's going to turn acidic. It's going to dissolve a whole bunch of nasty metals, cadmium, arsenic, et cetera, and all come out at this portal here. So, which is not a good thing, right? So, that consideration didn't enter their mind in 1960 when that tunnel was built. So now when it came time to close the mine, you really had two options, or Kinross had two options. One is to put an acid treatment plant right at the portal, in which case you would attempt to neutralize the acidic water coming out of the mine. That would drop out all this sludge and all the toxic metals. You'd gather that up and put that in storage, and you'd do that to the end of time. Or plan B was put in these three plugs, 1, 2, 3, and create what was called a mine pool. And the idea is that the water would then back up in the mine, keeping all the acid and the sludge and stuff in the mine. So that's the plan that Kinross went to. And I want to emphasize they didn't just go half-cocked. They consulted with the state agents, the regulatory agencies, and this is how these things were treated. Okay, so this is what they did in 1995. So now fast forward 20 years, 2015. Okay, now the mine next door to Sunnyside, called the Gold King, was making acidic water out through this adit here. Okay, and the EPA decided they wanted to put in a plug, just like they did at Sunnyside. Okay, the problem was by then the adit had collapsed, so you couldn't enter the adit. But it was still pushing out water, acidic water, and full of toxic stuff. So their plan was to open up the adit and then put in a bulkhead. Okay, fine. It turns out the EPA has a very detailed 5-page long protocol for how you're supposed to do this. And the short version is you drill a lateral small drill hole, and then you stick in an endoscope. And for those who don't know what an endoscope is, it's sort of like it's what they stick down. If you got ulcers and stomach ulcers, they stick it down your esophagus, and then they can look around and look at your ulcers. Okay, that was the protocol. That's the official EPA protocol. Do you think they followed their EPA protocol? Well, no. They got up a backhoe and let her rip, because after all, what could happen? This. Turn the river yellow for 70 some odd miles, all the way past the New Mexico line. Well, needless to say, the local population wasn't too happy with this turn of events. And, they got together with their pitchforks and torches and followed the yellow stream up. And there they found a bunch of EPA subcontractors looking very sheepish and like, oh, shit. So of course, this made national news. It's not every day you turn a river yellow for 70 some odd miles. There was a congressional hearing, which is how I know about the 5. I attended that hearing, by the way, and that's how I know about the 5 pages of protocol. And just as an aside, care to guess how many EPA people got fired over this? I mean, this is a rather serious screw-up. And the answer is 0. Okay, some people got some nasty notes in their personnel file, but anyhow. So the lawyers then got to work, right? So EPA first started to sue. They started to sue the owner of the Gold King mine, who's a geologist by the name of Todd Hennis, who happened to buy this thing at a tax sale. Okay, and not the best investment he could have made, but he was thinking exploration potential. Well, needless to say, Todd doesn't have a whole lot of money. He's the walking definition of small fry. So then the EPA went after the owners of Sunnyside, arguing that there's so much, goop and iron oxides, because most of this, by the way, is limonite. It's iron oxide, that it had to have come from the Sunnyside. Well, that was strongly contested, but in the end, I think it's probably correct that most of this stuff did come from the Sunnyside. But the owners of the Sunnyside, that's being Kinross, well, they have lawyers too, so they sued the EPA. And they basically argued in so many words that if the EPA weren't such a bunch of chuckleheads, this whole sorry incident wouldn't have happened. And that too, I think, is fundamentally correct. So ping and pong, it went back and forth, and the result being a $90 million settlement to be split 50-50 between the EPA, i.e. you, the taxpayer, and Kinross. So there's now $90 million in the kitty. They've now spent close to 40 doing studies and whatnot. They haven't yet. The idea is to build an acid treatment plant at the portal. They haven't done it yet. So you're now down to 50 million from the 90 million. I think the acid treatment plant's going to cost 2025, and your annual operating costs are going to be about 2.5 million a year. So you're looking at maybe you're going to get this water treated for 10, 12 years before they run out of money. And that's where it lies. And with that, I can refer you to this article, and I guess we'll throw it open for questions. None?
Are there any questions for Paul? Oh, Chris has got one.
Well, I'm just curious if any of those intrusive alkaline rhyolites are mineralized.
Did you hear that, Paul?
They're not, yeah, I'm having a little trouble. They're not mineralized. Well, let me put it this way. There are rhyolites. We saw some rhyolites at Mineral Point, but they're not mineralized. So you have rhyolites in the area, but they aren't mineralized that we know of. Okay. Again, the intrusive at Sunnyside, although all the evidence suggests there's one there, they haven't yet encountered it. Idorado, I believe, has a rhyolite as well, but those workings are collapsed and we can't access it. So the answer is we don't yet have the smoking gun.
Any more? Oh, Chris has one more.
Is the Sweet Home mine anywhere in that area?
I can't make that out. So Christine, can you?
Is the Sweet Home mine anywhere in that area?
Which mine?
Sweet Home?
No, Sweet Home is up near Alma, Colorado, which is central Rockies, long way away, totally different geology.
When talking about the age dates of the different deposits, how were they dated? Like what methods were used?
Most was done KAR. The USGS is going back and now doing some redoing of some of this stuff. Basically, what happened, just as an overview, was this. I was at the tail end of exploration there. In the 80s, and then once Sunnyside closed in the 90s, basically everybody lost interest. So there's been a 30-year gap where minimal work has been done in this corner of the world. And Mario, with his PhD, who started looking at this flashing and the B veins, really represents some of the first really new work. So, you know, if you're talking about isotopes or you're talking about age dates, yeah, we could have some revisions because you're looking at 30-plus-year-old dates, and as you know, the technology and methods have gotten that much better.
Any more? Okay, well, Paul and everybody, I think this concludes our meeting. Thank you very much, Paul.
Oh, my pleasure. I apologize for all the, you know, Zoom is never as satisfying as having a speaker there.
All right, well,
And,
yeah, thank you.
yeah, okay.
I'll talk with you later.
Very good. Take care.
Bye.
I'm going to leave now, unless you
Okay.
want some other questions or something.
Nope, I think everybody's done.
Okay.
All right.
We'll catch up later. Take care.